Okay, so we are moving on to this chapter, which is probably the most practically useful chapter in the chapter 3. We spent quite a time in the Carnot cycle is important and the introduction of the entropy is important. If you combine the internal energies and the entropy changes, you start to allow you to have concentrating on system. Okay? So there are two free energies, and one is called the Helmholtz free energy. The other one is well-known Gibbs free energy. Many people use a different symbol. They use in the Atkins textbook, they use an A. I think everyone used Gibbs free energy as a G, and there's no ambiguity. Sometimes the people using a different symbol for that. And what this is, let's talk about the definition. Helmholtz free energy is essentially combining U minus T times S. That's a Helmholtz free energy. Whereas Gibbs free energy is H minus T times S. So these are the definition. Okay? This is the definition, and there will be much more useful form of one, but this is a function definition as it is. Now, as you can see here, this is an internal energy, this is an enthalpy, right? So this is a more useful description under constant volume. This is under constant pressure. Okay? And so that's why finally, this one is much more relevant for more practical situation. And now, going back to second one, spontaneous changes. And remember, ds total, that's a spontaneous changes. Okay, yes. Actually, the other term that is called isolated system. That's the same statement, because the only true isolated system is a total. So this has been the spontaneous statement changes, and that one we didn't focus on the systems, right? But now we are focusing on the system, and first one, dA. So we are focusing on the system, on the constant temperature and the volume in a direction that you are reducing the Helmholtz free energy. Under constant temperature and the pressure, the system undergoes spontaneous change in a direction for Gibbs free energy goes to in a direction for the negative. And this one is a key, really a key to what we call chemical thermodynamics. Okay, so because it's a PChem course, chemical thermodynamics is important here, right? I think the mechanical engineer who's doing this more, I guess they have a different types of engine. We just touched the surface on the Carnot engine. There are different engines, diesel engine, auto engine. They all doing all kinds of heat transactions and work and efficiency. Whereas we are want to focus on chemical thermodynamics and under constant temperature, constant pressure, that's the direction for change. Now we can have a better understanding about how the chemical reaction is changing and at what condition does it attain to be an equilibrium, right? Equilibrium condition. And how chemists define the equilibrium constant, right? And equilibrium constant is defined, and eventually we want to, and that will be in the chapter, actually even later, is how the equilibrium constant, depending on the pressure, depending on the temperature, how we can manipulate the equilibrium conditions so that we can get more product out of this reaction, right? So I will take this one and give two examples here. So one example, actually this is one example. So I'm going to choose constant temperature. Right? So, and having G is an H minus Ts. So change in the G must be dH minus TdS minus SdT. All right? And then I'm going to say constant temperature means this is 0. So I ended up getting, probably you have seen this equation as well. dG is dH minus TdS. That means under constant temperature. And the entropy change and the enthalpy change is affecting both the Gibbs free energy changes. And when I actually was a student, I was always wonder, okay, dG must be in a direction for, way the dropping, right? The Gibbs free energy has to be, and that's a spontaneous process. And endothermic, this is what we empirically experience. Endothermic reaction, you guys know what that means, right? It is a reaction that heat absorbing. The fact that we call endothermic reaction means that's a spontaneous process for that. And how do we define the endothermic process? Your delta H is heat liberating or heat is absorbing, right? So it is a positive, right? Well, I will put dH is positive. This is the same notation. I'm just going back and forth. But think about it. I want to, when things naturally happen, this has to be negative, right? Well, endothermic, this is positive here. Not good, right? Not good. That's why what should happen is this guy with the temperature, this entropy change has to be, in a way, much big enough. So this term is a big negative compared to small positive. Right? So that's the idea. So that's why endothermic reaction is not so common actually if you look at that. A lot of things are exothermic reaction, and exothermic reaction we see it because that's a spontaneous process that we saw. So in a way, you want to develop this concept which is a balance between heat transaction, entropy change multiplied by temperature, and those are the balance between these two. So it is a battle between these two to whether it's going to happen or not, and that's really the balance that you need to figure it out. Okay? Exothermic is much easier. Right? This is already there. Exothermic, that's good. It's just a matter for this is already positive. If it is a positive reaction, then that's going to happen no matter what. Good.